So our goal is actually to explore how visualization, plotting, helps us think about data, to see variations in data. So let's start building on that. Suppose I want to display all 4 of the graphs of the different orders of growth all at the same time. Simple way to do it. I just call plot with each of those lists as the y values. The linear one, the quadratic one, the cubic one, and the exponential. And you'll know I'm keeping the same x values here because I want to have the same x coordinate. I just want to see what the different graphs look like when I call those. So if I were to execute this in my computer, I get a display like this. Not quite what I wanted. And that's part of what we want you to see. You can see here that there are at least 3 graphs overlaid. You can guess that this one out here is probably the exponential one. It's growing really fast. That is probably the cubic one. But you notice down at the bottom, what happened to the other 2 graphs? Well, in fact, it's impossible to see the linear graph here, or even, frankly, the quadratic one. If you look closely, you can see a very slight red line down there. And that's because the scales of these graphs change so rapidly. Remember, I'm graphing things with an x-axis from 0 to 29. So the linear graph only goes up to 29, and notice the scale here goes up to 140,000. That's part of what we want to look at. How do we change things so we can actually visualize data? And the first thing we can take from this is, boy, exponential grows really fast, and certainly a great deal faster than linear. Okay, how might we think about doing the display so we can see things a little bit better? As we said, it's not helpful because I can't see things because the biggest plot just grows too fast. So could I graph each one separately? And the answer is sure. I'm simply going to call another function called figure, and I'm going to give it an argument, and that argument simply gives a name to this figure. It's going to allow me to generate different windows, different displays for different graphs. And in fact, I'm going to be able to refer back to that figure if I want to do other things inside of it. Let's look at how that might help my problem here. Idea is that when I call plt.figure, if I call it with that argument for the first time, it's going to generate a new display with that name. If a display already exists with that name, it's going to reopen it and let me do additional processing inside of it. And let's look at an example. So here are my 4 calls to my plots, as I did before. In the previous case, I just called them all and they overlaid all those plots inside of the same graph or display. But now I've added a call in between each one of them, saying in the figure with name lin, I'm going to do the linear one. In a new figure with name quad, I'm going to do the quadratic one. And similarly for cube and expo for exponential. I'm creating 4 different displays, each one with its own plot inside. So that lets us then see things like this. Here, calling plt figure of lin, opened up a window or graph with the name lin, inside of which I plotted my samples and my linear. And I get that nice graph of a straight linear line with the range only going up to 30 because that was the maximum size of something inside of that graph. When I call plt figure with expo, that has now a new window with the name expo inside of it. And when I call plot of my samples and my exponential, it gives me a different graph. The range here is automatically set to be the largest value I need to show the same thing. That's 140,000. But now I can compare those 2 graphs. I can see the effects of these 2 different displays inside of each window without having them, if you like, buried one very tiny inside of a second one inside of the same window. So I could plot on separate graphs. That's nice. What else might I do? Well, we'll look at that in the next section.